Hello, welcome to another problem-solving video. In this video, we're going to be thinking about two blocks on an incline and just thinking about friction acting on those blocks. Is it going to be enough to prevent them from sliding down the slope? If not, then how are they going to move, with what accelerations? And then we'll think a little bit about work just in light of this problem, just to see how we can apply those concepts as well. So on the surface, this problem might seem a bit straightforward. We've got all the coefficients of friction, both the static and kinetic, and we've got the masses of the blocks. But then we realize, as we start to do this, there's a lot that could be happening. For instance, block A might sit still and then block B slide, or they might both slide. If they both slide, they might slide in such a way that block A slides slower than block B, so they slide separately, or maybe block A wants to slide faster, in which case it's pushing block B, and block B is holding block A back, and they slide together. So there's an awful lot of possibilities that we're going to have to check for. In order to do that, we'll need to figure out what the forces are on each block, and we'll start by basically working from that simplest assumption: is block A going to want to push on block B or not? That's the first question that we need really to answer. So we'll start off with a nice force diagram for block A. Block A will be this one. And what does it have? Well, it has gravity, which is acting straight down. Actually, it's got some normal force acting normal to the incline, and it's got some friction force acting at the slope of the incline. Now, it's actually this angle. So here's the incline. I'll just draw it in like that. Oops. Like that. This angle is the 35 degrees. So we can decompose gravity into two components. And this angle is also 35. Okay? Because I've taken this thing which was normal to this incline, and essentially I've rotated my coordinate axes in order to go from that to here. That's the same as rotating this one to there. So I know that this angle must be the same as that one. Okay, if you're ever not sure about these things, you can just imagine what happens if I make the incline really big. Well, then when I draw this thing, that would be the normal force, that would be gravity. I can see that it's indeed this angle, which has also become really big as I made the incline big. Right, it's not actually this other decomposition. So that's supposed to be perpendicular. So it's not actually this angle. That one's gotten smaller. So it cannot be this guy. It has to be that guy. That's my 35 degrees. And then I know, okay, I can decompose this. This is going to be basically force of gravity times the sine theta. So that's mg sine theta there, because this gravitational force is, of course, mg, and that's mg cosine theta. All right, so with that, we can start thinking about what forces, how these forces are actually balancing, and whether or not they are, in fact, because that's the question. If the net force is going to be 0, or can be 0, then block A is not trying to slide. So what is the friction force? Well, it's got a maximum. The maximum static friction is just given by the coefficient of friction times the normal force. What's the normal force? That's this guy. That's the force of friction. That was mg. That's mg sine theta, and that's mg cosine theta. Well, we know that we have actually balance of these forces that are perpendicular to the slope, because the block is certainly not going to fly off the slope or fall through the slope. So we know that the normal force must balance against this force, which is our mg cosine theta. So the maximum friction force is mu s mg cosine theta. So that takes care of looking at the perpendicular direction. And we've now got one thing which is acting along the plane, and we've got the other one sitting right here, mg sine theta directed downward. So we'll take that to be our positive direction. since that's the direction we might move in. So looking in that direction, we've got a positive force minus by this friction force, which is in the opposite direction, mu s mg cosine theta. So we know that the force on A is, at the moment, neglecting block B. We just want to see by itself, does it want to slide, or would it sit still? Because if it sits still, it won't push on block B. Block B won't actually push on block A. Block B will do its own thing independently. So let's find out what the net force on A is. Well, it's mg sine theta minus mu s cosine theta. Okay. Now, let's figure out what this value is. So m is 100 grams, which is 0.1 kilos. G we'll call 10. Okay, if you've got a calculator, you can use 9.8. If you don't, as I don't, we'll just use 10. Then we need to know something about sines and cosines. So fortunately, I've gone ahead and cheated and brought these into the video. So the sine is 0.6. Mu s, in this case, for block A, looking at that, is 0.5. And cosine is 0.8. And those two are multiplied. So we're looking at 10 times 1/10, which gives us 1. 0.6 minus 0.4. So just 0.2. But that's greater than 0. So block A wants to slide. Now what that means is, when we think about block B, we know that there's a normal force, a force by A on B, which we've just actually computed, a force of gravity, which decomposes in the same way, and a force of friction. So if we want to know if block B slides, well, then it's a little bit different to this equation here. So this was force on A. Force on B is the same thing, plus this force of A on B. And officially, that also means that really force of A has a term from B acting on A. But we don't need to worry about that one right now because we already know, well, we don't know if block B is actually going to stand still. If that force is too much, block B will actually slide down, and then we'll return to asking the question of, do they slide together or don't they? So let's take a look. And just work out what this suggests is going to happen. So because maybe if the friction on block B is large enough, which is possible, the coefficient is larger for static friction, maybe it's enough to stop B and A from moving. So the force on B, we've got a positive mg sine theta as before. We've got a mu s, this time of B, I'll just remind us that was A, of mg cosine theta. But then we have plus FAB also acting to push us down the slope. And that we found was 0.2 newtons. So I'll write that here so we don't forget. Okay, so again, we can pull the mg's out. So there's a 1, right, because of the 1/10 of a kilo times the 10 for g times the sine of theta minus mu sb cosine theta, and then plus this 0.2. So what's sine of theta? That's still 0.6. Cosine of theta is still 0.8. And mu s this time is 0.8 as well. So that gives us a negative 0.04, because 0.8 times 0.8 is 0.64. 0.6 minus 0.64 gives us negative 0.04. But then we've got plus 0.2. and just fill those spaces in. So add those two together, and we get 0.16 newtons of force acting, net force acting on B down the slope. So at long last, we know that they're going to slide. Okay, so then the question becomes, all right, they're going to slide, then what happens? Are they going to slide together? Is block A still going to basically be pushing against block B, or what's happening? So most of these things are the same. The friction forces and the forces acting by the blocks on each other are potentially different. Okay, and then should, in theory, be, if they're going to be acting, there'll be a FBA, which may be 0, but we'll draw it in. So in order to ask what's happening, again, we're going to start off by saying, let's pretend that the blocks are acting independently. Let's find out what they want to slide with, and then we'll adjust if necessary. So acting alone, the forces are those equations there, except we need to change all our static coefficients of friction into kinetic ones. So we'll quickly erase the s's, and we'll put some k's in. All right, so we know these numbers now almost by heart. The sine, 0.6, the cosine, 0.8. M times G just gives us a factor of 1. So in fact, we'll just get rid of those. Okay, so what would be our little net force on A? So F on A sine theta, which I said was 0.6, so let's go ahead and put that in, minus 0.8 mu k for block A, 0.2. So that's 0.6 minus 0.16. And that is, in turn, taking that one off gives us down to 5. Taking this 0.6 off gets us to 0.44 newtons of force. FB, without worrying about block A, is 0.6 minus its kinetic coefficient 0.3 and 0.8. Even without really doing the math, although we can, 0.6 minus 0.24, we realize that the friction force is larger on block B, so block B is going to want to slide slower. We can go ahead and put numbers to it. That's 0.36 newtons. They've got the same mass, so the acceleration of A, because it has a larger net force, is going to be larger. If the acceleration is larger, then it's trying to move faster. Its velocity would have been faster, except it clearly, therefore, pushes against block B. All right, so at this point, we now know they're going to slide, and they're going to slide together. So we need to know what the acceleration is. So now we do the last trick. If we know that two objects are moving together, then we treat them really as one big object. So we can write that the sum of the forces on A and B are going to be, well, there's going to be friction acting on block A and friction acting on block B. So we've got a mu k times an mg cosine theta for each block. Mu k b mg cosine theta. That's the friction forces. We'll have an mg sine theta for both blocks. That's the same. So we'll just go 2mg sine theta, acting on both of them. And the friction forces are, of course, opposing. And now that we're treating them as one block, we don't have to worry about the details. What is the force that B pushes on A? What's the force that A pushes on B? Those are inside our little system of the two blocks. So we don't care about that. We only need these external forces. So this trick of treating them together simplifies our life by not having to worry about how exactly they're interacting. Okay, so that's all the forces in this horizontal direction. And of course, if we want the acceleration, well, we know that this force, the net force, is equal to mg, where m, the mass of our combined object, is actually 2 times little m, because we've got 2 blocks moving together. So we can figure out, that's 2ma. We don't know what the acceleration is, right? Because essentially force is equal to mass times acceleration. The mass is the mass of both blocks together. So 2ma is equal to the sum of the forces is equal to this combination, because these are certainly the net forces. We've got gravity acting on both blocks, which gave us a factor of 2, minus the friction on either one. So then we'll put all this together. Okay, so therefore A is equal to, we can divide the m's out. We can divide by 2. We'll cancel there. And that gets an on 2, and that gets an on 2. So then we've got g cosine theta on 2 with a minus sign overall and a mu ka plus mu kb. And then a plus g sine theta. All right, so we're treating g as 10. I'll factor it out. So we've got 10 sine theta minus cosine theta on 2 with this sum of the kinetic coefficients of friction. So that's 10 times 0.6 minus 0.8 divided by 2, so 0.4. And the sum of the coefficients of kinetic friction, there's a 0.2 and a 0.3, so we get 0.5. Okay, should have had closed brackets there. So that's 10 times 0.6 minus the product of 0.4 and 0.5 is just 0.2. So that's 10 times 0.4, which is 4. Okay, and if you want, you can put in 9.8 again. You can do this out with a calculator. You'll get roughly the same number, right? Just a little bit smaller. All right, so now we know what the acceleration is. This is the acceleration of block A and block B because they move together, since block A wants to go faster but cannot because block B is there to hold it back. Okay, so they're going to go at 4 meters per second squared. Units are important. That's an acceleration. All right, so that is the first part of this question, and as advertised, we're going to turn it into something about work. But let's go ahead and clean the board, and then we'll pick up where we left off. All right, so now we've got a clean board. We've figured out the first part of this problem. Blocks move, they move together, they have an acceleration of 4 meters per second squared. So we would like to figure out, given that, how can we do some sort of work question? So let's take a look at what it is. What work does block A do on block B as they slide down the slope a distance of 1 meter? So we'll need a force times a distance, and the force should be the force by block A on block B. Well, we don't know that force, unfortunately, because we treated the system as one whole thing, but we can figure it out. We can look at just block B now, which is moving with this acceleration, and determine what happens to it. How does that arise? So let's think about that. The sum of the forces acting on block B should equal the mass of B, which is just m, times the acceleration, which is this 4, but it should also equal an mg sine theta directed down the slope, a minus mg cosine theta directed up the slope, times a mu. And then there's also the force of A acting on B, directed down the slope. So if we look at this, since they're both equal, we can rewrite it. F of A on B is equal to, we'll have the m times A, subtract an mg sine theta, and add an mg mu k cos theta. So then we can start putting in some numbers. 0.1 times 4 minus mg just becomes 1. Sine of theta is 0.6 plus mu k for block B is 0.3, and mg was 1, and the cosine of theta 0.8. So that is equal to 0.4 minus 0.6 plus 0.24. So the 2, 4, and the 4 give us 0.64. Subtract off 0.6, 0.04 newtons. All right, so now we've got the force by A on B. That's easy enough. Work. That's a constant force. That's just force times distance. They're exactly aligned. We move down the slope. Force is directed down the slope. So there's no factor from the sine of theta, the angle between the force and the distance. And so it's just force times distance. Distance was 1 meter, so it's a 0.04 Newton meters, which is actually a joule. So with that, we've actually figured out the force between the blocks as well as the work done. Okay, so that concludes this video. Hopefully you found it helpful.